Hello, this is Mr. Craig, and this is the second video of 2 for day 126 dealing with galvanic cells. We'll do some calculations similar to what we did yesterday, and then we'll also do some galvanic cell calculations. So let's get to question number 1. It says, answer the following questions using data from the standard reduction potential sheet at 25 degrees. So make sure that you get your standard reduction potential sheet out so that you can do this and do the homework. The conditions are standard, which again means that we are looking at 1 molar solutions. So number 1A, it says, is nickel plus 2 capable of oxidizing strontium metal to strontium plus 2 ions? And explain why. Alright, so to do this, let's first of all write out the equation so that we can make sure that we know that we're doing the right thing. So we have strontium metal, that's going to strontium plus 2. And the question even says that it's being oxidized. So there's our 1/2 reaction, which means that nickel that has a plus 2 charge must be oxidized since the strontium is being reduced. So since it has 2 electrons, we'll have 2 electrons on there, and it's changing to nickel. So the question is asking, will this reaction take place? Well, let's check and see. So let's find out strontium going to strontium plus 2. And strontium, where are you? Strontium near the bottom here. When strontium is reduced, it forms a negative 2.89, but since it's being oxidized in this reaction, we will write a positive 2.89. So we have a positive 2.89 voltage. So it's starting off well. And then looking at nickel plus 2 going to solid nickel, and it is being reduced. So find nickel. May have gone past it. Nickel, where is nickel? There it is, near the top here, where when it's reduced, it has a value of negative 0.25. So let's go ahead and write that down. So a negative 0.25. So obviously this reaction will take place since we have a positive value, and somewhere around 2.064, somewhere around there. Alright, and that is a positive voltage. So to answer the question, yes, nickel plus 2 is capable of oxidizing strontium to strontium plus 2 because we net a positive voltage, and that would be our explanation. Part B. Is iodine ions capable of reducing silver ions to silver solid? So let's go ahead and write that. Plus 1 to a silver solid, which means that it is being reduced here. Now, also recall, these reactions are not occurring in the same container. This is a galvanic reaction. So they're in their own separate chambers. So what we're looking at is, will the iodine ions be able to reduce the silver from plus 1 to solid by exchanging the electrons? So let's look at the iodine here, going from iodine negative to iodine. And if you're not sure which direction that's going to go, then we can obviously look at the equation sheet. Now, since iodine looks like I2, then we need to have 2 in front of it, which means that it is losing 2 electrons. Now think about this. Does iodine really like to be oxidized? Well, we'll see. So let's take a look at the silver value for the reduction of silver. And that's right here at 0.8. So we have a positive voltage to start off with. So 0.8 voltage. And let's look at the iodine, which should be very close in the neighborhood there. Here's I2 and 2 electrons. And when it is reduced, it has a positive voltage of a voltage that is a positive value. So since it's being oxidized, then that means it will have a negative voltage. So negative 0.53. And that will give us a positive voltage as well. So what is that? 27. So a positive voltage. Hopefully that number is correct. So yes, the iodine is capable of reducing the silver from a plus 1 ion to solid silver. Now again, recall, this is not a single replacement reaction. These are 2 separate reactions occurring in 2 separate chambers. So yes, this will take place. Okay. Let's look at number 2. It says, in a galvanic cell, the concentration of tin plus 2 is changed from 1 molar to 0.33 molar, and the concentration of the aluminum ions is changed from 1 molar to 0.47 molar, and the temperature is 25 degrees. All right, part A says, first predict the oxidizing agent and reducing agent for the spontaneous reaction in the cell. After that, determine the anode and cathode for this galvanic cell. Now again, recall that for a galvanic cell to operate, it has to be spontaneous, which means that we have to have a positive voltage. So what we have here is that we have tin, that's a plus 2, and we have aluminum, that is a plus 3. And from our standard reduction potential sheet, we have all reduction reactions here. So I'm going to start off with the reduction reactions. So we'll have 2 electrons will form solid tin, and 3 electrons will form solid aluminum. Now, yes, these are not separate equations. These are both reduction reactions. So what I want to do is I want to find the combination that's going to give us the most positive voltage. One of these will be oxidized, so I'll have to flip the equation, which means I'll have to flip the sign on the charge, and one of these will remain the same. So let's find out which one we should flip to get the most positive charge, so to speak. So looking at the tin, let's find tin. Where are you? So tin metal, I probably passed it already. There it is. So, that's a 10-4 to 2. Where's regular 10? Guys, where is it? There it is. Okay, sorry, right next to it. So when tin is reduced, it has a voltage of 0.4 or 0.14, and that's a negative sign. So let's look at the aluminum. And aluminum down here, when it's reduced, it has a negative voltage of 1.66. All right, so here's what we need to do. We need to figure out which of these reactions should be an oxidation reaction to give us the most positive voltage. Now, it doesn't mean that both of these are going to necessarily be positive in charge. They won't. In this case, they won't be. However, what we can look at is whichever one has the highest negative voltage as a reduction, we want to flip that one so that we get that to be our highest positive voltage. So what I'm going to do is I'm going to flip the reaction here. So aluminum, there. So what we're going to now write is aluminum metal wants to be oxidized. Actually, let's erase that. Move it over. Oop. So aluminum will go from aluminum metal to aluminum ions, and this will now be a positive voltage. So here we have our most optimum charges available, so this will give us a positive point, what is that, 252, I think. Okay, so there's our voltage, which is first predict the voltage for our spontaneous reaction. We did that. And then we want to determine who's the anode and who's the cathode. All right, so again, remember, anox, red cat. So who is being oxidized here? So the oxidation reaction is right here. So the aluminum is the anode. And the site for reduction, which is here, is my cathode. So the tin is my cathode, and again, it'll always be some form of metal that is either an anode or a cathode. It's not ever an aqueous solution. Okay, so here we have that. All right, so our anode, cathode, and we're good for the next B. Calculate the cell potential for the galvanic cell at standard conditions. Use the Nernst equation to show the standard conditions. All right, so here's our equation that we have to use. So looking at this balanced equation here, we have, actually, let me rewrite it. Clean it up a little bit here. I think I could probably clean it up by erasing some things here. So erase that, erase the circle. erase that, erase that, erase that, and that, and all that. We don't need those. Okay. All right, so here's our equation. So let's go ahead and write out our correctly balanced equation here for our total reaction. Notice that we have 3 electrons in this half reaction. We have 2 electrons in this half reaction. We have to have the same number of electrons to cancel electrons out. So since there's 2 on top, 3 on the bottom, we're going to multiply the top by 3 and the bottom by 2. So that gives us 6 total electrons. Remember, 6 total electrons for later on. And that will give us 310 plus 2 plus 2 aluminum, no charge, yields 2 aluminum, I have a plus 3, and 2 tin metals. Okay. So there's our overall balanced equation. That's what we need to have. Okay, so doing that, now we want to use the equation that we had from, let's see, where was it? Oh boy. It was, hang on, it was E, that was equal to E cell, that, minus 0.592 over N, and then it was a log of Q. Let me double check that. I'm going from memory here. I hope that's right. Sorry guys, I'm going to look at it real quick. I want to make sure that's right before I say anything else there. Open up. Open up. So all the way down from the previous video that we looked at. So this right here, the 0.0592, hopefully that's what I had. Yep, okay, so we're good. So again, this is the potential that we just calculated, the the positive 1.52 volts. So let's go ahead and write that in since we know that. Positive 1.552 volts minus 0.0592. And again, how many electrons did we exchange? We had 3 times 2 and 2 times 3, so 6 total electrons. And then we're going to take the log. We're going to take the log of Q. And Q in this case, let's go ahead and write the Q up. Again, Q is equal to the products over the reactants. No solids should be present. So we have aluminum that has, oops, sorry, I did want to put that in there, plus 3 charge. And it has a coefficient of 2, so that's our exponent. And then 10 with a plus 2 charge, and we have 3 of those. So that's our Q value. Now, what are our concentrations at standard? 1 molar and 1 molar. So square and cube those guys. So we have 1 squared divided by 1 cubed is equal to 1, and the log of 1 is 0. So 0 times all of this makes our voltage, that right there. So again, log of 1 is equal to 0, and then 0 times all of this causes the back end to be a negative 0. So our answer is, under standard conditions, the charges we get from our standard reduction potential sheet is our actual value there. All right, so now part B. Calculate the cell potentials of the galvanic cell under the new conditions, or the changed conditions. So it said that the 10 went from a 1 molar to a 0.33. So let's go ahead and do that. Let's go ahead and plug in our values. So again, E, positive 1.52 volts under standard conditions. 0.0592. Still have 6 electrons. And the log, and the 10 is on top or bottom. It's on the bottom. Is 0.33. Is it squared or cubed? It is cubed. So we have that one. And then the aluminum ions change to 0.47. So Plug that in, 0.47, and that is squared. So let's find out what that is. Okay, so 0.47 squared divided by 0.33 cubed is, on my calculator, 6.146. So take the log of the answer, and that gives me the log of all this equals 0.7886. I'm going to leave that in my calculator. Now I want to multiply that times the 0.0592 and then divide it all by 6. Wow, that gives a big change. So now what we have is the E potential is equal to 1.52 volts minus 0.00, just 2 zeros, 778. And again, that is a voltage change. So when we look at this, the voltage isn't going to change by that much. So 1.52 minus the answer, it's now a positive 1.51. Okay. Well, I think that's all the calculations for this. I hope this video has helped out. If you have any questions, don't hesitate to email me.